11th standard you have studied relation between wave velocity. For every 1 centimeter length, how many waves are present, which is represented as nu bar, is called as wave number. Electron from all higher energy levels jumps to the second orbit. The electron remains in the excited state. Hello students, let us move on and finish up the last session on the topic atoms. So if you recall my previous session, based on Bohr's postulates, we have derived an expression for orbital radius, orbital velocity, and the total energy of an electron in the nth stationary orbit of hydrogen atom. In my today's class, in my today's bookwork, we derive something called wave number of spectral lines in an hydrogen spectrum. So here in today's discussion, again a clinical 5-mark question, which is typically based on the 4th postulate of Bohr's theory. So using Bohr's theory, I will be deriving an expression for the wave number of spectral lines, again with respect to a hydrogen spectrum. Now, what is this wave number? Are you all familiar with something called as wave number? Please to understand, the reciprocal of wavelength, which is represented as nu bar, is called as wave number. So mathematically, wave number is represented as the reciprocal of wavelength. Hagidre, is spectral line andrenu? Many a times we have used this word spectral lines with respect to a spectrum. Yenit spectral lines andre? A spectral line is a line which indicates the jumping of electrons from one energy level to another energy level. No prime physics in it, no quantum physics in it. In simple terms to understand, a spectral line is a line which indicates jumping of electrons, transition of electrons from one energy level to another. So here I will be deriving an expression for wave number. So I will consider an electron which is in the ground state what I call as E1 of the hydrogen spectrum. So there is a electron which is in the ground state of the hydrogen spectrum, and I supply some external energy to this electron. On gaining this energy, the electron is excited now. It jumps to an excited state, what I call as E2. ಮಕ್ಕಳೇ, ಫಸ್ಟ್ ಎಲ್ಲಿತ್ತು ಎಲೆಕ್ಟ್ರಾನ್? ಗ್ರೌಂಡ್ ಸ್ಟೇಟ್ ಅಲ್ಲಿತ್ತು. ಅದನ್ನ E1 ಅಂತ ಕರೆದೆ. ಎಕ್ಸ್ಟರ್ನಲ್ ಎನರ್ಜಿ ಸಪ್ಲೈ ಮಾಡಿದಾಗ ಎಲೆಕ್ಟ್ರಾನ್ ಎಕ್ಸೈಟ್ ಆಗುತ್ತೆ, and it excites or jumps to a higher excited state E2. Please to remember, maybe an atom or an electron remains in the excited state for a very small interval of time. How long? Nanoseconds. The electron remains in the excited state for a very, very small interval of time, nanoseconds. Then it has to come back to the ground state. It has to lose its energy. It loses its energy in the form of radiations, photons ಅಂತ ಕರಿತೀವಿ, and it comes back to the ground state. And therefore, the energy of the photon h nu is equal to E2 minus E1. Now, going back to yesterday's derivation, energy of an electron was derived as E equals minus Z minus M Z square e to the power 4 N square H square epsilon naught square. Kindly recall in my last session where I derived expression for total energy. E equals minus M Z square e to the power 4 divided by N square H square epsilon naught square. So in this expression, all terms remained constants except for N. So substituting here, E2 minus E1. So all other terms remains constant. E2 ಅಂತ ಬರೆದಾಗ orbit number is N2. E1 ಅಂತ ಬರೆದಾಗ orbit number is N1. Therefore, h nu is now written as M Z square e to the power 4 divided by 8 H square epsilon naught square. And rearranging the terms, illi nodi, minus 1 by N square, this is minus of minus 1 by N square, so this becomes plus. Therefore, I have written 1 by N square minus 1 by N2 square. Now, I want wavelength term to come into picture, because very clearly I told reciprocal of wavelength is called wave number. For a wave, we usually write V equals F lambda. 11th standard you have studied relation between wave velocity and wavelength. V equals F lambda. Similarly, for a radiation, electromagnetic radiation, speed is c, frequency is nu, lambda is kept as it is. So here, nu becomes equal to c divided by lambda. Generally, for a wave, V equals F lambda. Radiations are speed is c, frequency is nu, wavelength is lambda. So nu equals c divided by lambda. So I am substituting nu as c divided by lambda, which is mz square e to the power 4 8 h square epsilon naught square 1 by n1 square minus 1 by n2 square. Now left hand side alli ಏನು ಇರಬೇಕು? I am defining reciprocal of wavelength as wave number. So I want reciprocal of wavelength. So I just keep 1 divided by lambda, reciprocal of wavelength, and take h and c to the denominators. So h square ide, one more h will make it h cube, epsilon naught square, and what is coming back here? It is c. So h into h square h cube. This c also comes to the denominator. And here, this 1 by lambda is represented as nu bar and it is called as the wave number. So simplifying this expression, 1 by lambda is nu bar is equal to, all these constants are replaced by r, 1 by n1 square minus 1 by n2 square, where this r is called Rydberg's constant. These expressions, constants within the highlighter which is replaced by r, is called Rydberg's constant, whose value is 1.097 into 10 power 7 lines per meter. And now we substitute Z equals 1 for hydrogen. Therefore, wave number is defined as the number of waves present per unit length of the spectrum. For every 1 centimeter length, how many waves are present? That is called as wave number. And now coming to the last topic of discussion, we study something called hydrogen spectrum. ನೋಡಿ ಇಲ್ಲೊಂದು ಬ್ಯೂಟಿ ಇದೆ. Hydrogen has only 1 electron, but transition of that 1 electron, jumping of that 1 electron from one level to other, is giving me 5 different series. ಒಂದೇ ಎಲೆಕ್ಟ್ರಾನ್ ಟ್ರಾನ್ಸಿಷನ್ ಒಂದು ಎನರ್ಜಿ ಲೆವೆಲ್ ಇಂದ ಇನ್ನೊಂದು ಎನರ್ಜಿ ಲೆವೆಲ್ಗೆ ಹೋಲಿಸಿದ್ರೆ 5 ಸ್ಪೆಕ್ಟ್ರಲ್ ಸೀರೀಸ್ ಸಿಕ್ಕುತ್ತೆ. Then just imagine uranium 23892 where there are 92 electrons. That is why it is called a complex spectra. So the 5 series present in the hydrogen spectrum is the Lyman series, the Balmer series, the Passion series, the Bracket series, and the Fun series. Very important. You need to know the empirical formulas here. Problems, yes, this time I'm expecting very much from this chapter. So first, Lyman series. Lyman series is formed due to the transition of electrons from higher energy levels to the first orbit. Very clearly you see the formation of Lyman series here. From all higher orbits, electrons jump to the first orbit, and this spectral series constituted is called Lyman series. Lyman series ಯಾವ ರೀತಿ ಉತ್ಪತ್ತಿ ಆಗುತ್ತೆ? ಎಲ್ಲ ಹೈಯರ್ ಎನರ್ಜಿ ಲೆವೆಲ್ಸ್ ಇಂದ ಎಲ್ಲ ಹೈಯರ್ ಆರ್ಬಿಟ್ಸ್ ಇಂದ ಎಲೆಕ್ಟ್ರಾನ್ ಫಸ್ಟ್ ಆರ್ಬಿಟ್ಗೆ ಜಂಪ್ ಮಾಡುತ್ತೆ. ಹೈಯರ್ ಎನರ್ಜಿ ಲೆವೆಲ್ಸ್ ಇಂದ ಟ್ರಾನ್ಸಿಷನ್ ಆಫ್ ಎಲೆಕ್ಟ್ರಾನ್ಸ್ takes place to the first orbit, which is actually constituting the Lyman series. So, from all higher energy levels to the first orbit. And this series lies in the UV region of the spectrum. ಇದನ್ನ 1 ಮಾರ್ಕ್ಗೆ ಎಕ್ಸ್ಪೆಕ್ಟ್ ಮಾಡಬಹುದು. Which region of the electromagnetic spectrum does Lyman series belongs to? UV region. Or which region of the spectrum is present in the UV region? Lyman series. Now this is important. For any given series, the value of N1 is fixed. So for Lyman series, N1 is 1 because transition is happening to the first energy orbit. So N2 will be the next higher orbits 2, 3, 4, 5, etc. And we are also asked to write the empirical formula. We have derived 1 by lambda is equal to R 1 by N1 square minus 1 by N2 square. Empirical formula andre N1 substitute ಮಾಡಿ N2 na generalize ಮಾಡಿ. So N1 is 1, N2 is N. So this is the empirical formula for Lyman series. Next one, Balmer series. This series is formed due to the transition of electrons from all higher energy levels to the second orbit. So very clearly you see Balmer, from all higher energy levels, transition is happening to the second orbit. Electron from all higher energy levels jumps to the second orbit. Balmer series is formed. And here there is a very unique thing with Balmer series. It lies in the visible region of the spectrum. Balmer series is present in the visible region, and hence each line is identified by a name. First line is called H alpha, second line is called H beta, third line is called H gamma. So this is present in the visible region. Here N1 is 2, transition is happening to the second orbit. N2 is 3, 4, 5, etc. And this is the empirical formula. N1 2 agide, N2 generalize agide. Passion series. This series is formed due to the transition of electrons from all higher energy levels to the third orbit. It lies in the near infrared region. N1 is 3, N2 is 4, 5, 6, 7, and this is the empirical formula. Bracket series, transition from all higher energy levels to fourth level, middle infrared region. So N1 is 4, N2 is 5, 6, 7 and 8, respective empirical formula. Fun series formed due to the transition of electrons from higher energy levels to the fifth orbit. N1 is 1, 6, 7, 8 and empirical formula. So my dear students, we have discussed in detail the hydrogen spectrum, the 5 series of hydrogen spectrum, their empirical values and empirical formulas. And here I have got 2 definitions as assignment for you all. Please do refer your textbook. Get the definitions of these 2. One is called ionization energy. The next one is called excitation energy. Both these I would like you all to perform as an assignment. So in this chapter, as I have told, we have made an attempt to understand the structure of an atom, which means the properties of electrons. Next, we start up with dual nature of matter and radiations, something which is related to photoelectric effect. Until then, revise well, stay safe. We will meet next. Thank you.